Good evening, everyone, and welcome to our video on piecewise functions. Tonight we're going to talk about what exactly piecewise functions are, how we graph them, and how we evaluate them as well. So for some of these, we've actually kind of seen examples of them already, and especially when we were doing problems where we're talking about whether a function was increasing, decreasing, or constant, we saw functions that would have been considered or defined as piecewise functions. So sometimes we'll see these graphs where they don't look exactly like the ones that we have in our packet on the library of functions, but they look like combinations of them. So when we're combining two or more of these different functions that we know from our packet, we're going to call them piecewise functions. And when we define a piecewise function, we're always going to define the parts over certain intervals. So we're going to define for certain x values, the functions are going to adopt different equations or different functions. So down here in orange, we have an example of a piecewise function. So if I look at it, I see that there's three other functions from our packet. There's a constant function, a square function, and a square root function represented in this picture. But together, all in orange, that would be considered a piecewise function that we could call f of x. Now, if you want to pause it here and try to identify which function is which, give you a little practice on identifying which ones are constant squares or square roots, you could do that now. Otherwise, I'll move through it and highlight which is which. So first of all, which part is the constant function? Well, a constant function is a horizontal line, so it looks like from here to here would identify our constant. Then let's look for a square function. Remember, a square function is a parabola. And it looks like I have part of a parabola from here to here. Okay, so it doesn't include the whole parabola, but part of it. And then finally, the square root function, remember, looks like a parabola on its side. So that looks like this part of our function f of x is the square root function. Okay, so we've identified where this f of x is partially made up from these different functions here. So I've identified that on the graph. But now when we define a piecewise function, we're going to want to identify specifically what intervals represent these different functions. So we're going to be writing this, we're not going to use set notation or interval notation, but I do want to identify the intervals. So if we were to use interval notation to identify where we have our square root function, our square function, the blue one, it's from the x values from negative infinity over here, right, all the way to -4. And so I could use that. I'm going to include this green dot. I'm going to put that with the constant function. So you'll see sometimes these are connected and overlapping, or sometimes there's a gap. But let's say that the square function, the blue one, the parabola, goes from negative infinity to -4. Okay? That would be interval notation. But we want to get in the habit of, because we're going to define this function and the pieces using just greater than or less than signs and for our values for x. So I would say another way to write negative infinity to -4 would be x for all x values that are less than -4. Okay, so that would include all of the x values this way on the number line or on the x-axis. So not including -4 because I'm going to put that with my constant function. So it's the square function where x is less than -4. For the constant function, that's going to be from -4 inclusive to 2 exclusive. So if I were to use interval notation, I would say -4 to 2. Or if I use the notation that we're going to use for defining piecewise functions, I would say -4 is less than or equal to x which is less than 2. So that's another way to say all the x values between -4 included, so I have the less than or equal to there, between -4 and 2, it's going to be open. Okay? And then the last one, the square root function. If I want to write the interval on which this piecewise function is defined as a square root function, I would say from 2 included off to positive infinity if I was using interval notation. But in this case, another way that I'm going to write it is to say for all values of x that are greater than or equal to 2. So it includes 2, and then all x values that are greater than or equal to 2 are going to be defined by this square root function. So this kind of notation is what we're going to use to define the interval of the different pieces of a piecewise function. So when we write out a piecewise function, we are going to write out the different equations that make up the different parts of the piecewise function. And we include them in like one giant brace. And then we also have to identify the intervals that these separate equations are graphed on. So I'm going to have the graph of x minus 1 for all x values between -5 included and 0. Then I'm going to have the function f of x equals 3 graphed for all the x values between 0 included and 1. And then I'm going to have the function f of x equals x squared graphed for all the x values that are greater than or equal to 1. So we identify the intervals on which each equation is graphed, and then we're going to also later on, from now on, I'm going to refer to these as partial functions. So these separate partial functions together form an entire piecewise function f of x. So they're not like separate functions on their own, they're just together combined to make this one function f of x. Okay, so if I want to graph this, the easiest thing to do is to set up a table for each of the partial functions that make up this piecewise function, and just keep in mind what x values we can have in our table. So if I set up a table for each one of these, I have x, x minus 1, and then we'll have x, and then f of x equals 3, and then we'll have x and x squared. I'm going to keep an eye on my intervals here to see what values to plug in for x. So here I have from -5 included to 0. So if I plug in -5, pick a point in the middle, -3, and then we could put 0, but just remember that that's going to be an open point. So -5 minus 1 is going to be -6. -3 minus 1 is -4. And 0 minus 1 gives me -1. So these points are going to represent f of x on that interval. So -5, -6, -3, -4, and 0, 1. It's a good idea when we're making the table to use the endpoints of the interval so that we'll have an idea of what the graph looks like between there. So x equals 3 from 0 to 1. Okay, so this is a constant function. So when x is 0, the function is 3, f of x is 3. And when x is 1, f of x is 3, and that's going to be an open point. So I'm going to draw like a little open circle next to this to remind me that those are open points because of the inequality that I see there. And now for x, for f of x defined as x squared, I'll plug in 1, 2, 3, should be enough, and it'll keep on going because this is for all values x greater than or equal to 1. So at 1, 1 squared is 1, 2, 2 squared is 4, and 3, 3 squared is 9. So now I have 3 tables. They represent my 3 intervals, my 3 different partial functions, and together if I graph these, I will have an entire graph of f of x. And so I'll take all of these points and plot them down here on my graph. So I have -5, -6, So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. All right, I plot that point and it's filled in. Then I had the point -3, -4. And so that would be -3, 1, 2, 3, 4 down there. And then I have 0, -1. So 0, -1, and that's an open circle, remember? So now I can connect these with a line, and now I have one part of my piecewise function graphed. So I have the function x minus 1 defined over the interval -5 inclusive to 0, that's graphed. Now I have to graph f of x equals 3 over 0 to 1. So it's a constant function. The point is 0, 3 is right here, and then 1, 3 is open. So I have just that little stretch of a constant function. Then I have x squared, and that's defined for all values greater than or equal to 1 for x. So I have the point 1, 1, and that's going to be closed because it's when it's greater than or equal to there. Then I have the point 2, 4 right there, and then I have 3, 9 up there. So it's this stretch of a parabola like that. So this is my piecewise function, and notice that we have these different bounds that are of the interval that are either greater than or equal to, or you'll notice some of them are open. And remember, we want to call this, we want to define these so that they are functions. So we want this to still pass the vertical line test. So if I were to draw a vertical line here, it's going to go through that open dot and then hit a filled in point right there. So if this was closed up here, it wouldn't pass the vertical line test because it would run through 2 points, right? So we want to make sure if we're going to make up one of these on our own that they still pass the vertical line test when I draw a line. So that's what a piecewise function can look like. Sometimes these will be connected, and then sometimes they will be like gaps between them. So here you go from your x minus 1 function, and then there's a gap up to x equals 3, and that, or y equals 3, and then there's a gap over here to my parabola. So that's what these look like. And the easiest way to graph them, set up tables, and then use your intervals to help you fill in your table values. And just keep in mind which dots are open and which ones are filled. Okay, so we said we can graph these. We can also evaluate them. So we can evaluate a piecewise function for different values of x. The biggest thing to keep in mind is just that if I'm evaluating this for a different value, make sure you're plugging it into the appropriate partial function depending on what the intervals are. So if I have g of x here, and then I want to find g of 0, g of 1, and g of 2, I want to identify which one of these functions here I'm supposed to use when I evaluate these. So g of 0, that means x equals 0, right? Because g of x equals 0. So which interval contains x equals 0? So this is the interval -3 to 1. So x equals 0 would fall in there because it's between -3 and 1. So I'm going to use -x plus 1 to evaluate g of 0. Then let's look at g of 1. So g of 1, x equals 1. So I'm looking over here. X equals 1 is going to be, I'm going to use this constant function. And then finally g of 2, that's x equals 2, so check which interval that falls under. That would be x greater than 1, right, because 2 is greater than 1. So when I evaluate g of 2, I'm going to use the x squared as my partial function to evaluate. So g of 0 equals, I'm plugging this into this partial function, so -0 plus 1. The opposite of 0 is just 0, so 0 plus 1 is 1. So g of 0 equals 1. Then g of 1, I'm plugging into this constant function. So g of 1, no matter what, is a constant function, so it's just telling me that the function value here is 2. So g of 1 equals 2. And then third, g of 2, I need to plug that into this partial function, x squared. So I'm going to plug in 2 squared, and so g of 2 equals 4. So the biggest thing with this is you're evaluating functions just like you did before. You just got to figure out what x is and then what interval that falls under as to which partial function to use to evaluate it. Okay? So we'll leave it off there. We'll give you this one to practice on your own if you'd like to and bring it into class tomorrow. So find h of -1, h of 0, and h of 3 if h of x is defined as this piecewise function. All right, you can bring this to class. Have a great night, and I'll see you tomorrow.